Okay, let's finish this problem here. So this is my Lagrange's equation because it's only one variable really that represents the configuration of the problem. So I spell it out in terms of theta, and we were going to find the partial of r bar with respect to theta. And we said that with Lagrange's equations, the rate of change of things in time is with respect to an inertial reference frame. So it is assumed that here we mean g. And we drop that. But also the partials with respect to the coordinates, everything is referred to the inertial reference frame. So if I am sitting in the inertial reference frame, which is the one in which the big E's are fixed, the ground, and this I think we called it A, and this we called it B, with an angle theta that changes, I do see both of those vectors changing, right? So I just need to find the expression of those in terms of the big E's so that I see basically theta showing up, right? Well, that should be not a huge deal. ER is, what is ER? So this is my angle theta here, right? So it's cos theta big EX plus sine theta big EY. Agree? Sounds right. And then I want to go back to my sketch here just to make sure before I do UR. This is ER, this is E theta, and we said that rotating by an angle phi, I see my UR here. And so UR is equal to what? Sine phi E theta minus cos phi ER. Yes. Yeah. Okay, and then I have to do another step for this one, right? Because I want to go back to EX and EY. And so I have a sine of phi, which is multiplying now E theta, which is E theta is, let's see, it's cos minus cosine of theta EX. Not sure. Oof, okay. No. What is this angle here? This is pi over 2 minus theta, right? Okay, and so if I project on EX is minus cosine of that angle, cosine of pi over 2 minus theta is the sine, so it's minus sine of theta EX. Yep. And then the cosine of that angle, I'm sorry, the sine of the angle, sine of pi over 2 minus theta is cosine, so I have cosine theta EY. Do we agree? Yeah. And then minus cosine of phi ER, I already have it there. Cosine of theta EX plus sine of theta EY. So in this parenthesis I have E theta, and this is ER. Another sanity check to see if these two are correct. I'm pretty confident about this. If I'm not confident about E theta, well, a good sanity check is doing the dot product. They need to be at 90 degrees, right? That doesn't give me the certainty 100%, but this at least tells me that they're perpendicular. If I dot this vector here with what I have in parentheses here, I do get indeed 0, right? I have cosine, sine with a minus, sine, cosine, the plus, they go away. So they're definitely perpendicular, and hopefully I got the right direction with with that. So, okay. So it will become a little ugly again when you go to Lagrange's equations. You're trading you're trading for more calculations, but you don't need to deal with the constraint forces. And so what I'm really caring about now is that partial. So in the end, my R bar will be R minus R, and I want to quickly move to a new problem now because this is getting old already. Cosine of theta big EX plus sine of theta big EY plus L this. Sine of theta, I'm sorry, sine of phi minus sine of theta big EX plus cosine of theta big EY, and then I have minus cosine of phi, which is multiplying cosine of theta EX plus sine of theta EY. So that is, except simplifications that you can make, and the fact that theta and phi are actually related to each other by the relationship we just wrote previously, which, if I'm not mistaken, is phi equal this, right? Big R over little r theta. That is a nightmare, and that is why when you're doing dynamics for real systems and multi-body systems, you really need to use tools that are computer-based. That's why I'm not going to give you problems that involve more than one or at the most two rigid bodies in specific, manageable configurations, because otherwise they become lengthy calculations. There's nothing you can do about that. But I hope that at this point you know how to do this, right? We know how to do this. I can start saying that this is equal to, well, that's a constant, and here I have minus sine of theta EX plus cosine of theta EY plus, I should probably change all those phis. Why not? Theta. Oh, it's going to be a little ugly here. Okay. And what else here? Okay. And I keep going. This is L. Okay, what do I have in here? I have a R, big R over little r, cosine of the same, multiplying all these, plus the sine of r over little r theta, multiplying the partial of that now, which is a minus cosine of theta big EX minus sine of theta big EY. And then I have minus cosine there, so that gives me a sine. Okay, gives me this term, big R over little r sine of the same argument, with the parenthesis as it is, plus, actually minus, cosine r big R over little r theta, and the derivative, the partial of that with respect to theta, which is minus sine of theta EX plus cosine of theta EY, and good luck with that. Well, it's really not that ugly, because remember that what you need to do is now mg dotted with this. I mean, of course, you can manipulate these and simplify things, but well, this ends up being mg is what? Is mg EX dotted with this terrible expression. So you can pretty much take what you see and throw away everything that has a EY. It's a dot product, right? And so you only retain the terms with the EX. Yes, I mean, it still be a little ugly, but doable. I hope you don't want me to do it. because
one of them cancel.
I'm sure that some cancel. Yeah, I think many cancel each other here probably. For example, I see. Let me see. Probably here. I didn't write what's inside, but what's inside here is that minus sign. It's exactly what you see here, right? Except here there is a factor capital R over little r, so probably not. Well, you get what you get, but that's how you would do it.
What happens is you go back to the first function, you see you have sine r over little r theta, and then on the EY direction you have sine times cosine positive, and then minus cosine times, oh no wait.
Yeah, when you do the partials of these, unfortunately, you get this extra term here that, yeah. So, once again, I hope you understand now that none of what we've done can be removed from your memory, and you see why I give you, again, that much time, because things get longer to solve. More complicated maybe, but the principles are really just a few. It's just that a simple geometry like this can give you long calculations. But I do care about you setting up the problem right. If you make mistakes here, well, yeah, it's a mistake. But this is not a class on algebra. Okay, so can we move on? Are we all clear with this problem? Can we do another one which is even worse? Probably. Well, it's not that it is worse. The rigid bodies involved actually have a nicer geometry. There's no weird offset center of mass. But there are two moving rigid bodies now, even though one does not rotate. And I really want to discuss the problem before we solve it, which is what you should do in your mind before you start writing things down. So we have this, and this is 524 is the one of your colleagues suggested or was trying to work through. So we have, this is a first rigid body. It's, I don't know what to call this, a rectangle that has had some mass removed here so that you can have a circular, semicircular track, and has a mass capital M, and it's moving on ground without friction. No friction. Okay. And then inside this, so the center of this semicircular guide here is O. There is no mass here, right? So this is the mass. Okay. I have another disk. This time is a regular disk, which is a uniform disk, so it's a rigid body. The center is called P. Its mass is little m. And let me define a few things here. Point of contact is Q. That's O. The angle between the vertical direction, there is gravity here. The vertical direction and OP is called, it's very similar to what we've seen before. This is called theta. And then I pick a point on the rigid body on the edge, and I call that K. I don't think the book gives it a name, but I am here. And so this other angle is phi, very similar to what we had before, except this is now a uniform disk. Okay. Radius of this is little r. Radius of this is big R, as before. And there is roll with no slip between big M and little m, the two rigid bodies. And I want to find the differential equations of motion. One more thing that you're given if you look at the book. Again, this is problem, I think it's 524. This is what I have in my notes. I think it's 524. You're also given this variable x that tells you the position of, well, basically of the point O, of the big mass M as it slides horizontally. Now, you're asked to find the equations of motion of these. In terms, I think the book actually gives you a lot, the text of the problem gives you a lot of hints and directions, because it asks you to find the equations of motion, I believe, in terms of x and theta. So when you read a problem like this, you're already given, first of all, that this problem has 2 degrees of freedom. If they're asking you to find the equations of motion in terms of x and theta, those are your 2 degrees of freedom. The parameters, 2 of the parameters, a combination of 2 parameters that can give you the configuration of the system. So it's a lot of work has been removed for you by giving you this. And as you can imagine, similar to what we've done with the other problem, the theta and phi are not really independent because there is a roll without slip. But try to think about the case where you could be given something like this, rigid body m, rigid body little m. I'll tell you there is a roll without slip, and I just ask you find the equations of motion, nothing else. I'm not going to give you theta, phi, x, nothing. You have to find them yourself. That's what will happen in your life. That's what probably some of you are doing for research. You're not given heads up. You're not given some suggestions. You have to define things yourself. So these problems are actually simplified in the sense that you're given already the degrees of freedom here, and the variables to use. But do we agree these are 2? Well, m can only translate on this ground, so that's obviously 1 degree of freedom. And then the second rigid body has a roll without slip condition, and we already said that if we think about the simpler case where you're rolling on a flat surface, this is a 1 degree of freedom problem, right? So 1 plus 1 is 2 degrees of freedom. Okay. Now, you can do things in many different, well, not many, 2 different ways probably. Euler's laws, classical Newtonian mechanics, and Lagrange's equations. Okay? Now, before I even start, I want to remind you one thing that we have seen before entering chapter 5, rigid bodies. We've done systems of particles, and if you recall, we had one example where we had, wow, this is really not straight at all. Well, even worse. Well, fine. We had this wedge and a block on top of it, right? We were not even doing rigid bodies. And I said, I'm going to treat these as particles and apply, and do the free body diagram of these, and then the free body diagram of these, and then of the system altogether. And when you do the system, the internal actions, reactions, they don't count. Well, you can do it here too. When we dealt with particles, when I started finding that expression that summation of all external forces is equal to m total mass of the system acceleration of the center of mass with respect to some inertial reference frame. And when I started doing these, particle 1 with mass 1 and particle 2 with mass 2, all these drawings, and I said, okay, they exchange equal and opposite forces. Well, yes, they're particles, but I never said that these cannot really become rigid bodies, almost, that they can have mass distributed around them. The principles that we've seen still apply. So I'm just giving you a hint that at some point, if you start writing equations of motion and you find yourself with not enough equations, where you can look at this as a system, as we've done here, and figure out what is the free body diagram of the entire system. You can do that. This will still count. Does it make sense? They are 2 objects. They are exchanging from an external point of view. If I look at this as a system, big M plus little m, they are 2 objects exchanging action and reactions according to Newton's third principle. So each action has an equal and opposite reaction. So when I look at them from the outside, whatever happens between the 2 is not my concern. That doesn't go into my system's free body diagram. So you can do that if you need it. Okay? Just an important comment, I think. Well, let's start trying to attack this problem the classical way, the Newtonian way. Okay. What is it that we do? Well, we first of all figure out the reference frames, right? I do see here, in principle, a couple of rotations, even though they're related to each other, as we'll find out. But as we've done with the other problem, I can probably define a reference frame which is the plane perpendicular to the board that contains OP. So that allows me to describe this, it's associated with this first rotation, and then the same, another plane perpendicular to the board which contains P and K, that's the second rotation. And as we said, it's better be safe than sorry. You can also add an additional reference frame, which is the mass M that it's translating. That's a rigid body, it's moving, it can be a reference frame. If I won't use it later on, no, not big deal. So G is the ground, right? That's definitely one of them. And well, you're given X here, so you can say that the origin of these is O at time equals 0. Remember that O is actually moving with respect to the ground. It's the center of that guide, right? Okay. And then, well, EX as given. There's not much else to say. It's there. What do you want to do? I almost want to do EY as minus GY, because this will give me, this should give me EZ, which is of course EX cross with EY. It should give me EZ coming out, right? Yeah. And so I see this first rotation, that theta dot will be positive about that, but I mean, it doesn't matter if you do it the other way. It will not be incorrect. So this will be my EX, EY, and EZ, and this is fixed to the ground. Okay. Now M could be another one. So let's call that, I want to call that A is the mass M, the first big object there. We can say origin at O. Now O is moving, and these are the same, right? It's not rotations here. So I mean, it may be useful. Who knows? If it's not useful in the end, who cares? It's an additional reference frame. It's basically the same as the ground coordinate system. It's just allowed to translate. The origin is, and it's moving. Okay, and then let's call B the plane perpendicular to the board containing OP. Right?
Just make the other bets.
Yeah, that will be the next. Yeah. So I said, since I see initially two rotations here, I'm going to associate a reference frame to each rotation, right? So yeah, the next one will actually be the mass. Yeah, the second mass. Yeah. Yeah, and then we do origin at what do you want to do? O is fine for that one too. No? I think so. And as before, let's do ER along OP. Is it OP? Yeah. And then EZ, okay, now we want to do EZ equal to big EZ probably. And then as a consequence, E theta would be EZ cross with ER. So this is exactly as before. Now this drawing is becoming a little messy here. ER is like this, E theta is this way, EZ is this way. And then the last one, so this is what I call B. So let me write. This is ground. This I called it A. This is fixed in B, which is not an actual physical object. And then the last one will be again a physical object. So C is the disk, yeah. And I can say that has an origin. That's a good idea. It needs to be fixed. Fixed to the actual rigid body, so P, right? And then as before, you are along PK, and then UZ into page, just because I see that that phi angle is as a sign opposite to theta, so it makes sense to go into the page, but you don't have to. And u phi is going to be uz cross with ur. And so this other coordinate system is the following. ur is this way, uz goes in, u phi goes this way. Okay. Pretty similar setup to the other one, right? Okay, so those are my reference frames and coordinate systems. And now, if I'm using Euler's laws, I need to do kinematics. Actually, you have to do that anyways, no matter what you do. Kinematics. I have two objects now, so let's do the easy one. The kinematics of the first mass. The position of the first mass of m is x(ex), and so its velocity is x dot ex, and so its acceleration in g, of course, is x double dot ex. I'm not going to spend much time on that, right? That's easy. So that's the kinematics of the first object. Yeah, not too bad. Now, what about the second object? So this was for m. What about little m? Now, what is the position of the, remember these are rigid bodies, so I'm thinking about the center of mass of this. Oh, by the way, I'm going a little too quick here. This is supposed to be bar, bar, bar. When we do rigid bodies, we look at the center of mass, right? And so if the mass of this is uniformly distributed, it should be pretty obvious that the center of mass is somewhere along the symmetry axis. It's not O, because there is no mass up here. It would be O if it looked like a donut with a weird shape, but there is no mass there. So it's below O, somewhere on this line. So I'm only caring about this motion because I do know that there is really no motion along Y. So that it's kind of incorrect. Well, if you want, I can fix it by saying that the position of the center of mass for that mass is xex plus some y bar ey, but this is constant. It is not changing. So when I go to the first derivative and second, it goes away. Okay. 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 So now what do? I do what do I do? The second one. So I need to find r bar for the little mass, the disk. What is that? Well, that would be what do you think? RO plus big R minus little r ER. Right? Make sense? So the origin of the ground fixed coordinate system is some point here, O. I want to call it O. What do I call it? I don't know. Q, which is O at time equals 0. So say that this big mass was there with the point O here at time equals 0, and then it moved somewhere else. So that is where I'm counting things from, right? I set that up. I said the origin for the ground fixed coordinate system is O when t equals 0. So it's whatever this point was at t equals 0. Say that it's down here. So, and now I want to tell what is the position of P with respect to the point. So it's this RO vector, right? I go from here to here, plus this vector. I go from O to P. And that's what I just written here. So velocity of little m, the center of mass of little m, with respect to the ground will be the rate of change of this. Now, what is this? The rate of change of this. What is it? and then I'll take care of the second one. But can you tell me what this is? X dot EX, right? It's the same. Okay. So I have x dot EX, and then this is, what do I do here? Same old story, transport theorem. This vector is fixed in B, so I will just say that this is omega B with respect to the ground cross the vector itself. What is omega of B with respect to the ground? Is theta dot EZ, which is crossed with r minus r with the vector itself. So this is going to give me, what is EZ crossed with ER? EZ crossed with ER is E theta. So this is what I have. Okay. And then, this needs a little more space. The acceleration of m with respect to the ground, the center of mass of m, is, well, x double dot EX should be really a no-brainer. And now I'm taking the rate of change of these with respect to G again. So now if I still work in B, I will have d dt in B of this. And what is it? That's a theta double dot r minus little r E theta, right? Plus what I've done before, omega of B with respect to G, which is theta dot EZ, cross with the vector itself, theta dot r minus little r E theta, which is going to give me x double dot big EX. That remains whatever it is, theta double dot r minus little r E theta. I have EZ crossed with E theta. Is that ER? That's minus ER, right? Minus theta dot squared ER. Okay, fine. I'm done with kinematics, almost. I'm not going to simplify this or do anything with it. That's what it is. What I haven't used is, and this is still part of kinematics, is my roll without slip condition. So I have the kinematics of m, the kinematics of little m. I just have to use that condition. What does that tell me? The velocity of q as part of, what did I call that? I called the reference frame A, right? As part of A, which is the big M, as seen by A, for example, is equal to the velocity of q as part of, what did I call this? C, right? Yeah, C in A. This is 0, right? And so 0. Okay, I know that the velocity of q as seen part of the disk in A is 0, but this is equal to also what? Tell me what that is. This is the same exact thing we've done with the other problem. I want to find basically a relationship between theta and phi. I really need to erase stuff here. Think about it while I copy this. Do you know what to do? Remember what we done last time? Point P, the velocity of point P can be expressed in different ways. The velocity of point P with respect to, now, I don't want to do things with respect to the ground. I want to do everything with respect to A. I seat myself in A because it's easier to see what's going on. So if I see P as being part of reference frame B, right? Part of that plane, how do I write its velocity with respect to A? So now I'm sitting in A, and I see that basically this point going in a circle around O. how would you write that? That's the rate of change in A of the vector that goes from O to P. So it's basically Rp with respect to O. Okay? Which is also the rate of change with respect to A of which vector? What is that? That's R minus little r ER, right? Okay. But little er is changing in A. I'm picking up the speed, I'm sorry. But that, do you see that? Little er is changing in A. It's part of B, it's fixed in B, not in A. So this is equal to d dt in B of this, which is 0, by the way. Okay, 0, plus the angular velocity of B with respect to A cross with the vector itself. Okay, and what is that? The angular velocity of B with respect to A is, again, theta dot little z, which is crossed with R minus R ER. Okay, EZ crossed with ER is EC theta, right? Okay, we should get the same thing that we had before. Really, I'm just redoing the same stuff. So, but now, so I know that VP can be expressed that way. Okay, fine. It can be also expressed in another way. And what is that way? Can you tell me? P is part of the disk. And I do know that there is a relationship between the velocity of P and velocity of Q. The velocity of P as part of the disk, which is C, as seen by A, minus the velocity of Q as part of the disk, as seen by A, and this, by the way, is 0, because I proved it to be 0, okay, is equal to omega what? Which one? This is now C A crossed with Rp minus Rq, right? And what is this? What is the angular velocity of C with respect to A? Theta dot minus phi dot, little z. Stop me if you don't agree. Cross with, what is Rp minus Rq? It's minus little r ER. It's the vector that goes from Q to P. Agree? Okay. And now EZ crossed with ER. Haven't we just done it before? Yeah, I think we've done it before. So this is minus R theta dot minus phi dot E theta. Am I making a mistake with the sign? It doesn't look like, right? Yeah. Okay. So these are the same velocity, though. It's the same point. And that's your relationship. You can, so basically this is your relationship between the two. This is equal to this. I think it's the same one we got before with the other problem. Do you see an error? I think it's right. Tell me. This is a property of the rigid body, right? When you have a rigid body, the velocity between 2 points and the accelerations between 2 points have a relationship, and that is what we are doing here. So I'm looking at point P and point Q as part of the disk, which is what I call reference frame C. And so the difference in their velocity is equal to the angular velocity of their reference frame with respect to the inertial reference frame, which I picked to be the observer, A, cross with the vector that goes from P to Q. I'm sorry, cross with the vector.
I'm confused by it. So that is point, the velocity of point P as seen by somebody in C.
No. This is the velocity of point P as seen now as a point belonging to C, seen by an observer fixed in A, the same that I did before. Before I just looked at P as part of B, which is not a physical object for us, it's just a reference frame, which is that plane containing OP. There must be, it's the same point. It is the same point. Yeah. It's not like the point where the roll occurs that has all those points overlapping to each other. That's just the same point. It is, if you think about it, P during motion, the way I define the reference frames, P will always remain in this plane, which is reference frame B. It will always be part of that plane, and it will always be part of the disk C. So it does belong at the same time to the two different reference frames, two different rigid bodies, if you like, where one has an actual mass and the other one doesn't. And so my end for kinematics is really that these formulas here, the acceleration of the center of mass of the two objects, and these are the relationship here, which is telling me, let's simplify this. I see a theta dot. I think it's the same exact one that we had before, right? This goes away. Yeah, it's the same one. So we can just reuse the same. It's saying that phi equals capital R over little r theta, given the correct initial conditions. And if they're not all zeros, you will have other constants in there, but that's really not the point here. So this is my kinematics. That's where I'm going. That's almost. What am I missing for kinematics? This is rigid bodies. What am I missing? When you think about rigid body, kinematics, what do you need to do? Velocity of center of mass, acceleration of center of mass. Then, just think about one rigid body. Then, what else do you do? A rigid body can translate and rotate. How about this? Need to find this. So for M is really no-brainer. Let's not even think about it. That object is translating. It's 0. Capital M. 0. H bar, with respect to the ground, for little m is, what is this? This is the inertia tensor of the body, which I called C now, with respect to the center of mass, dotted with the angular velocity of C with respect to the ground. And that is really, do I have to do it? Yeah, that's the angular velocity. Okay, fine. And what else? What would be the general thing that you would do here? You would do I RR in this case, right? RR ER. Oh, that's UR. I'm sorry. UR circle cross UR plus I phi phi U phi circle cross with U phi, etc., etc., etc. Okay, and there is also the other terms. But then, so let me actually write this with UZ for a second. So with UZ would be this way, right? But then this is applied to omega, which you told me is something UZ. So the only terms that survive here are which ones from the inertia tensor? This is a planar problem. The Z one. So this is really whatever that is. I don't even want to remember the formula. Is I ZZ bar. And you can go and look up in a book what is the moment of inertia about the center of mass for a uniform disk, with respect to the axis of symmetry in this case. Okay. Fine. Now I'm done with kinematics. I'm going to put it down here. H bar in G for little m, I don't need to write that. That's the only mass that is really rotating, is I ZZ bar phi dot minus theta dot little uz. Okay. Kinematics is done. I start with kinetics. Recycling part of this. Free body diagrams. What happens to this object? And this object. Let's start from this one. This has uniform mass, so center of mass is the center of the disk. There is mg here. And then I see some reaction from the track, and then it's rolling with no slip, so there is some force of friction, static friction, same as before. The only difference is that the center of mass is now the center of the disk, and h is not 0. That's what happens to this one. This other object has gravitational force applied somewhere at its center of mass, mg. Some reaction, let's call it ng, to indicate that that's from the ground. And that's it, there is no friction from outside. But then here, depending on where the other object is, I have minus f sub f, right? And minus n. And remember, you have to tell me that these are the minuses of these, because there is actual reaction involved. So if you call in that f sub f, these other objects is minus f sub f. And same goes with n. Okay. Well then, I can start writing equations of motion. Or maybe the first principle of Euler, right? The first law. Let's look at this one. I have mg plus n plus f sub f is equal to little m, its acceleration, that expression up there. So I have x double dot little ex plus theta dot r minus little r e theta minus theta dot squared er. Fine. Let's leave it at that for now. For the second object, I see mg plus this reaction that I don't know, minus n minus f sub f equals capital M x double dot ex. So this one indicates first law of Euler. Is this enough to find my equations of motion? Remember, I need two. I have way too many unknowns here. 3 reactions that, n, ng, f sub f, that I have no idea what to do with. And by the way, this goes for this problem as it did apply for the wedge and block problem. Even though these are 2 equations, remember these are vectors in a plane. So these are 2 equations, these are 2. You may think that they're 4, but they are not independent. If you start manipulating them, they're not independent, because we haven't done the free body diagram of the entire system yet. But let's pause on that for a second. I still have to use this one, right? Second law of Newton, of Euler. Okay. Now, which one is the general form for a generic point? d dt in G of h q in G is equal to, I don't remember this. I refuse to remember this. Can you remember it? The general one. The one that collapses to the nice expression when you have center of mass or inertially fixed point. Which one is it? mq minus r bar minus rq cross with m a q in G. I'm just writing down the ingredients that we would have in general, right? We know these, and we also know that if you want to move your angular momentum to another point Q, and you have it at the center of mass, which is why we computed there right away, this is what you have. This is little m, yes. Do they sound familiar? You derive this. Don't memorize, just know they exist. And look in the book at the end, angular momentum, and go to the right page. Now, I have this. If I choose my point Q to be an inertially fixed point, which is probably not a great idea here, this will collapse to an expression like this. d dt of hqg is Q becomes an inertially fixed point, or the center of mass the same, or if I don't want to, I keep this term. And the moment I move from center of mass to another point, I have to also find h with respect to that point by using this expression down here. So what do you want to do? You now have to pick a point. This will give you another equation, but and I'm looking, of course, at the disk. There is no such an equation for the big M, because there's no rotations for that mass. There is no correct answer. It's just you picking a point rather than another one. What will be convenient? My goal here is getting rid of these n f sub f and g.
Point Q.
Point Q sounds like a good idea, because n and f sub f will go away. So you will only have the mg term in here. But then you will have to find the acceleration of Q in the inertial reference frame. That's why we'll probably, well, we continue this, but this is one of those cases where Lagrange's equations, oh yeah, you really may want to use those, just because you may have less calculations or not, I don't know, but you don't have all these unknown reactions to deal with. So if we pick Q now, well, we need to find the velocity of Q in G. Now, by picking Q, I mean what? What Q?
The Q on the disk.
The Q on the disk. Okay, so that's 0 then. Is it? Is it 0? It is 0 as seen by an observer that is sitting on this mass here, right? That it's moving with big M. But is it 0 with respect to the ground? Because I see that I need to compute it. V bar, I have it. I erased it, but I did compute it. V bar is fine, I have it.
No, it's not 0 with respect to the ground.
And what is that? You can tell me right away what that is. X dot dx, right? Yeah, because it's the velocity of m. So basically I'm breaking this as the velocity of Q in m plus the velocity of, I don't know how to call this. What did I call this? The velocity of the center of mass in G, right? Is that right? Velocity of Q in m. Well, I'm sorry. The velocity of Q with respect to m in G plus the velocity of the center of mass of that object. Make sense? So in other words, this point has no velocity seen by an observer fixed in A. So the only thing that is creating, that is generating velocity for that point is the fact that A is actually translating with respect to the ground. So that's what you have. Well, that's nice. Okay. Is that correct? You guys don't seem very convinced, right? So what was the roll? Yeah, what was the condition of roll without slip? Yeah, we should finish this next time. Vq in C as seen by A is the velocity of Q in A as seen by A. Okay. So this is 0. But what do I do with this? Because I want the velocity with respect to the ground. So I'm not sure if this is right. Because if that was right, then the acceleration of that point, what would that be with respect to the ground? Just x double dot ex? Yeah. As part of the disk? Sounds strange. Right? Think about this. We'll continue this next time. I guess I'll push the inertia tensor stuff to Monday.